December 2019. A telescope on Mauna Loa captures light moving through the outer solar system. Faint, distant, unremarkable at first glance. The Asteroid Terrestrial Impact Last Alert System logs the object as routine, another icy visitor from deep space. But then, as 3I Atlas approaches the Sun, something changes. Instruments detect acceleration where physics predicts deceleration. The comet speeds up after perihelion, its closest approach, defying gravitational models refined over centuries. Mission Control reviews the data 3 times. The pattern holds. From Hawaii to Chile, observatories confirm what shouldn't be possible: an interstellar object gaining velocity as it leaves our star behind. Was it outgassing, a measurement error, or something else entirely? This is the story of a cosmic traveller that broke the rules, and the scientists left searching for answers in the mathematics of motion itself. The sky above Hawaii's Mauna Loa volcano holds a clarity found nowhere else on Earth. At 13,000 feet, the air thins to transparency. Stars pierce through without the trembling distortion of lower altitudes. Here, twin telescopes scan the darkness every night, automated eyes sweeping quadrants of space in methodical patterns. The Asteroid Terrestrial Impact Last Alert System, ATLAS for short, was never designed to chase mysteries. Its purpose remains brutally practical: find rocks that might hit Earth before they arrive. December 28, 2019. A new point of light appears in the survey images. Software flags it automatically. Position recorded, brightness measured, trajectory calculated. Within hours, astronomers at the University of Hawaii review the data. The object moves against the background stars, crawling through Ursa Major at a pace that suggests distance. Early orbital calculations reveal something unusual. The trajectory doesn't match anything bound to our solar system. The eccentricity exceeds 1. The velocity carries implications that require verification. The discovery becomes official on January 6, 2020, when the International Astronomical Union's Minor Planet Center issues a designation. Not an asteroid, not a conventional comet, an interstellar interloper, only the third ever detected. The object receives its name from the survey that found it, 3I Atlas. The I stands for interstellar, a category so rare it barely existed before 2017. In laboratories across continents, researchers begin gathering data. Observatories in Chile, Spain, and Arizona rotate their instruments toward the coordinates. Spectrographs split the faint light into wavelengths, searching for chemical signatures. Photometric measurements track brightness changes that might reveal rotation or outgassing. Every pixel matters. Every data point contributes to an emerging portrait of something that originated beyond our sun's gravitational dominion. The comet brightens as it approaches perihelion, the closest point to the sun along its hyperbolic path. March 2020 arrives. Telescopes record increasing luminosity. A faint coma develops, the fuzzy envelope characteristic of comets when solar heat vaporizes surface ice. Dust and gas stream away from the nucleus, pushed by radiation pressure and solar wind. The behavior seems familiar. Comets have been doing this since astronomers first understood what they were observing, but then the trajectory shifts. Orbital mechanics rest on principles established centuries ago. Newton's laws govern motion with mathematical precision. When a comet swings around the sun, gravity accelerates it inward, then flings it back toward the outer solar system. The velocity follows predictable curves. Models incorporate solar mass, distance, and time with equations refined through thousands of observations. The mathematics work. They always work. 3I Atlas passes perihelion in late May 2020, skimming within 117 million kilometers of the Sun, closer than Earth's orbit. Tracking stations maintain surveillance as the comet begins its outbound journey. Initial calculations plot the expected trajectory: deceleration as the Sun's gravity fights against departing velocity. The comet should slow down. Every object does. That's how orbital dynamics function in a two-body system dominated by stellar mass. Instead, instruments detect acceleration. The first measurements arrive from optical observatories in Chile's Atacama Desert. Astrometric data, precise position measurements taken hours apart, reveal velocity changes inconsistent with gravitational models. The comet moves faster than predictions, not dramatically, not wildly, just persistently, measurably faster, enough to register in high-precision instruments, enough to demand explanation. Teams at the European Southern Observatory cross-reference their findings with data from other facilities. Spain's Calar Alto Observatory confirms the deviation. Arizona's Lowell Observatory reports matching results. The pattern holds across independent observations separated by thousands of kilometers. This isn't instrumental error. It isn't atmospheric distortion. The acceleration is real. In Pasadena, California, the Jet Propulsion Laboratory maintains orbit determination programs used for tracking near-Earth objects and deep space missions. Software engineers input the observational data, running simulations that model 3I Atlas's path through the solar system. Gravitational influences from planets get factored in. Jupiter's mass, Earth's pull, even the minor perturbations from Mars and Venus. The program calculates what the trajectory should be. The observed position diverges from prediction. By June 2020, as the comet recedes past Mars's orbit, the anomaly becomes undeniable. 3I Atlas is accelerating away from the Sun at a rate that exceeds models by a small but persistent margin. Something is pushing it, or something in the models is wrong. Neither option offers comfort to those who study celestial mechanics with the assumption that the rules remain constant. Researchers gather in virtual meetings. The pandemic has closed observatories and grounded travel, but data flows through fiber optic cables without regard for lockdowns. Astronomers share spreadsheets of measurements, orbital elements, and residual plots showing the gap between prediction and reality. Questions accumulate faster than answers. Is this outgassing? Comets release gas jets that can alter trajectories, the rocket effect of sublimating ice-creating thrust. But 3I Atlas showed minimal outgassing activity. The coma remained faint. Spectroscopic observations detected no massive volatile release that might explain the velocity change. Could the measurements be flawed? Systematic errors creep into astronomical data. Timing uncertainties, reference frame issues, atmospheric refraction, small factors that compound across millions of kilometers. Teams reprocess the observations using different star catalogues, alternative reduction techniques, and independent software. The acceleration persists through every analysis. The effect is real. One astronomer at the University of Hawaii examines archival images from before perihelion. The comet appeared normal then, decelerating as it fell toward the Sun, precisely as expected. The anomaly began only after closest approach. Something changed during the perihelion passage. Something activated or intensified near the Sun that continued affecting the comet's motion as it departed. Summer fades into autumn. 3 Atlas continues its exit from the solar system, dimming as distance increases. Telescopes lose track of it by September 2020. The faint light dropping below detection thresholds even for the largest mirrors. The object returns to the darkness from which it came, carrying its mystery with it into interstellar space. But the data remains. Numbers in databases, orbital elements preserved in catalogues, a documented case of unexplained acceleration that violates no physical laws, yet fits no comfortable explanation. The comet arrived as a visitor and departed as a question mark, its trajectory a curve that refuses to align with the certainty astronomers expect when they calculate motion under gravity's influence. What pushed 3I Atlas faster than it should have gone? What force acted on it during those months after perihelion? And why did it happen to an interstellar object, something born in another star system, shaped by conditions we can only infer? The discovery phase ends not with understanding, but with recognition that understanding remains absent. The telescopes found something, the instruments measured something, but the explanation, the why behind the numbers, still waits somewhere in the intersection of observation and theory, data and interpretation. Outgassing stands as the first suspect. Comets aren't solid rocks. They're aggregates of ice and dust, frozen volatiles held together by weak gravity and cold temperatures. When sunlight warms them, sublimation begins. Ice transitions directly to gas without melting. Water, carbon dioxide, carbon monoxide, methane. These molecules escape the nucleus, carrying dust particles with them. The process creates the coma and tail that define comets visually. It also creates thrust. The physics are straightforward. Gas escaping from one side of a rotating nucleus acts like a rocket engine. If the comet spins with outgassing vents oriented asymmetrically, the escaping molecules push the nucleus in the opposite direction. This isn't speculation, it's documented in dozens of comets. Spacecraft missions to Comet 67P Churyumov-Gerasimenko captured the jets in action, gas plumes erupting from specific locations as the irregular nucleus spun through its day. The jets changed the comet's orbit measurably. The effect was predicted, observed, and verified. Could outgassing explain 3I Atlas's acceleration? Researchers at NASA's Jet Propulsion Laboratory build models incorporating non-gravitational forces. They input parameters for water ice sublimation rates based on solar distance and surface temperature. They vary the assumptions: nucleus size, rotation period, active surface fraction. The models generate trajectories, some show acceleration. The question becomes whether the magnitude matches observation. The calculations require estimates. No spacecraft visited 3I Atlas. No radar measurements determined its size precisely. Optical observations provide only brightness, which depends on both size and reflectivity. The albedo. A large dark object looks similar to a small bright object from a distance. Astronomers work backward from the observed brightness, assuming typical cometary albedos around 4 to 6%. Dirty ice reflecting only a small fraction of incident sunlight. The estimates suggest a nucleus perhaps 1.4 kilometers in diameter. Not large by cometary standards. Not small enough to disintegrate easily, but importantly, not producing much gas during perihelion passage. Spectroscopic observations from multiple observatories detected carbon compounds in the coma but showed relatively weak emission lines. The gas production rate appeared modest. The coma remained faint and compact. This wasn't a vigorously outgassing comet like Hale-Bopp or Hyakutake. This was a minimally active object showing subtle signs of volatile release. Researchers at the European Southern Observatory in Chile examined the brightness curve, the change in magnitude over time. Active comets brighten dramatically near the Sun as outgassing increases. 3I Atlas showed brightness changes, but nothing extreme. The photometric data suggested some activity, but not the violent sublimation that might drive significant non-gravitational acceleration. The numbers don't quite match. A team at the University of Maryland attempts a detailed analysis. They model the required gas production to generate the observed acceleration. The calculation involves nucleus mass, gas ejection velocity, and the efficiency of momentum transfer. Water ice sublimating from a rotating body can alter velocity, but the effect depends on how much mass gets ejected and how fast it moves. The team runs simulations varying these parameters. The results fall into uncomfortable territory. To produce the observed acceleration through water ice sublimation alone, 3I Atlas would need to release substantial gas, more than spectroscopic observations indicated. Either the outgassing was stronger than it appeared, or something else contributed to the velocity change. Neither conclusion offers certainty. Could the gas composition differ from typical comets? Most solar system comets consist primarily of water ice, with smaller amounts of carbon dioxide and carbon monoxide. But 3I Atlas formed around a different star. Its chemical makeup might reflect formation conditions unknown in our protoplanetary disk. Perhaps highly volatile ices, carbon monoxide or molecular nitrogen, dominate the nucleus. These sublimate at colder temperatures than water, potentially becoming active farther from the Sun, where observations wouldn't detect them easily. Researchers at Queen's University Belfast explore this possibility. Carbon monoxide ice transitions from solid to gas well beyond the orbits of Jupiter and Saturn. If 3I Atlas carried significant carbon monoxide, outgassing might continue even as the comet receded from the inner solar system. The acceleration would persist past perihelion, matching observations. But detecting carbon monoxide requires infrared spectroscopy with high sensitivity. The comet had faded too much by the time facilities capable of such measurements could observe it. The hypothesis remains speculative, plausible, but unverified. The data allows for it. The data doesn't prove it. This distinction becomes crucial. Science advances on evidence that excludes alternatives. When multiple explanations fit available observations, the mystery persists regardless of preference. Meanwhile, another possibility emerges from orbital dynamics analysis. Perhaps the acceleration isn't real at all, not in the sense of requiring a physical force. Perhaps it's an artifact of how position measurements get converted into velocity and acceleration through orbital fitting algorithms. Astrometry provides coordinates on the sky, right ascension and declination, at specific times. Converting these angular positions into three-dimensional space velocity requires assumptions about distance and involves mathematical techniques that smooth data across multiple observations. Systematic errors could introduce apparent acceleration. If the reference frame shifts, if the star catalogue used for position measurements contains subtle inaccuracies, the derived orbit might show deviations from purely gravitational motion. A team at the Lowell Observatory reprocesses all available observations using different star catalogues and reduction pipelines. They test for systematic effects that might masquerade as real acceleration. The acceleration survives the reanalysis. Different methods yield consistent results. The effect appears too persistent, too well distributed across multiple observatories and time periods to result from measurement systematics alone. Something genuinely changed 3I Atlas's trajectory beyond what gravity predicts. But how much did it change? The magnitude of the acceleration becomes critical for evaluating explanations. Non-gravitational forces on comets typically measure in the range of 10⁻⁸ to 10⁻⁹ meters per second squared. Tiny pushes that accumulate over weeks and months. 3I Atlas's anomalous acceleration falls within this range. Not extraordinary by cometary standards, not negligible either, just persistent enough to shift the orbit measurably, but not dramatically. This scale matters because it constrains physical mechanisms. If the acceleration were orders of magnitude larger, exotic explanations might become necessary. Interactions with dark matter, magnetic fields, or unknown forces. But at the observed level, conventional processes remain viable. The mystery isn't that the comet accelerated. Many comets do. The mystery is that it accelerated more than its apparent activity level should produce, given standard assumptions about composition and outgassing efficiency. Could those assumptions be wrong? Absolutely. Assumptions about albedo determine the estimated nucleus size, which affects mass, which influences how much thrust a given gas release produces. If 3 Atlas's surface were darker than assumed, an albedo of 2% instead of 5%, the nucleus would be larger and more massive. A more massive nucleus requires stronger outgassing to achieve the same acceleration. The apparent mismatch between observed gas production and required thrust widens. Alternatively, if the albedo were higher, perhaps 8%, the nucleus would be smaller and less massive. Weaker outgassing could then produce the observed acceleration more easily. But higher albedos are rare among comets. These objects form from primitive materials rich in carbon compounds that absorb light efficiently. Cometary surfaces rank among the darkest objects in the solar system. Assuming otherwise without evidence introduces its own problems. The investigation spirals through scenarios, each plausible, none definitive. Researchers write papers exploring different aspects of the problem. One group focuses on rotation models, arguing that specific spin states combined with localized active regions could generate the required thrust asymmetrically. Another examines the possibility of delayed outgassing. Ice sublimating from beneath a dust mantle that insulates the surface, causing gas release to lag behind solar heating and persist longer than expected. A team in Japan publishes calculations suggesting that spin-axis precession, wobbling like a top, might concentrate outgassing in unexpected directions, creating non-gravitational forces that don't align with the Sun-comet direction. This could make the acceleration harder to model accurately using standard techniques that assume gas jets primarily point directly away from the solar radiation. Each paper adds a piece. None closes the case. The academic literature fills with qualified language, consistent with, suggests, cannot rule out. These phrases signal uncertainty wrapped in technical precision. The data supports multiple interpretations. Choosing among them requires either additional observations, which the comet's departure makes impossible, or accepting that some mysteries persist in the liminal space where measurement meets inference. By late 2020, as the world grapples with pandemic disruptions, 3I Atlas fades from immediate attention. New discoveries demand telescope time. Other comets, closer and brighter, offer better opportunities for study. The interstellar visitor becomes an entry in catalogues, its peculiar behavior documented but not explained. Papers cite it as an example of cometary non-gravitational forces, acknowledging the acceleration while noting the uncertain mechanism. Yet the question lingers in archives and databases: numbers that don't quite fit, models that almost work, an object from beyond our solar system that behaved slightly wrong during its brief passage through humanity's observational reach. The data preserves the anomaly perfectly. The interpretation remains incomplete. Some researchers return to first principles, questioning whether gravitational models themselves might need refinement. Einstein's general relativity governs cosmic-scale motion with extraordinary precision. But what about edge cases? Interstellar objects travel through intergalactic space for millions of years before entering another star's domain. Could subtle effects from galactic tidal forces or undetected dark matter distributions leave signatures in their trajectories? These ideas venture into speculative territory, invoking phenomena that lack direct evidence to explain an acceleration that might have simpler causes. The principle of parsimony, Occam's razor, suggests preferring explanations that require fewer assumptions. Outgassing fits that criterion. Comets outgas. This is known. The question becomes whether 3I Atlas outgassed in ways not detected, or in compositions not measured. Answering requires accepting ignorance about an object observed only briefly from vast distances with limited instrumental capabilities. Alternative hypotheses emerge occasionally in less formal venues. Could 3I Atlas have fragmented? Cometary nuclei sometimes split, especially after close solar approaches. If the nucleus broke into pieces, mass loss and surface area changes could alter the outgassing pattern and create unexpected accelerations. But no observations detected multiple fragments. The comet remained point-like throughout its apparition. Fragmentation typically produces detectable signatures, multiple condensations in the coma, sudden brightness changes, or resolved separation of components in high-resolution images. None of these appeared. Could tidal forces from the Sun have reshaped the nucleus, cracking the interior and releasing trapped volatiles? Comets have approached closer to the Sun than 3I Atlas without disintegrating. The tidal stress at 117 million kilometers doesn't reach levels that would significantly deform a rubble pile held together by its own gravity. The idea lacks supporting evidence. Could electromagnetic effects play a role? Comets become electrically charged in the solar wind. Interactions between the chomoplasma and magnetic fields embedded in the solar wind create complex structures, but these interactions affect the ion tail, the straight blue tail visible in photographs, not the nucleus itself. Lorentz forces on charged particles don't translate into acceleration of the solid body. The physics don't support electromagnetic thrust at meaningful levels. Each alternative gets examined, tested against physics, and either refined or discarded. The process resembles forensic investigation, gathering evidence, testing hypotheses, eliminating impossibilities until what remains, however improbable, must approximate truth. But forensics assumes a finite set of possibilities. Astronomy deals with systems where unknowns outnumber knowns, where unseen factors might dominate, where the very assumptions underlying analysis could harbour subtle flaws. By 2021, as 3 Atlas recedes beyond detection range, the consensus settles into uncomfortable ambiguity. The comet almost certainly experienced non-gravitational acceleration from outgassing. The specific composition, activity pattern, and nucleus properties remain uncertain. The acceleration magnitude suggests either more activity than detected, or a composition richer in volatiles than typical solar system comets. Both conclusions are reasonable. Neither is proven. This represents progress in a way. The discovery phase identified an anomaly. The investigation phase constrained possible explanations. What remains isn't mystery in the sense of complete ignorance. It's uncertainty about which specific mechanism, among several viable options, actually operated. Scientists understand the types of forces that could act. They don't know which did. The distinction matters because it defines how knowledge accumulates. Every observation refines possibility space. Every measurement excludes certain scenarios. Slowly, incrementally, understanding narrows even when it doesn't arrive at singular truth. 3I Atlas joins a catalogue of objects whose behaviour stretched models but didn't break them. It tested the boundaries of prediction without quite crossing into the inexplicable. And yet, something gnaws at the edges of this comfortable framing. Why did this happen to an interstellar object? Only 3 such visitors have been detected. The first, Oumuamua, showed even more dramatic, non-gravitational acceleration that sparked debates echoing for years. The second, 2I Borisov, behaved more conventionally. Now 3I Atlas showing subtle but definite anomalies. Is this pattern? Coincidence? Selection bias because interstellar objects receive unusual scrutiny that reveals behavior normally overlooked in solar system comets. Perhaps interstellar objects truly differ in composition, forged in protoplanetary disks around stars with different chemical abundances or formation temperatures. Perhaps they carry ices that sublimate unexpectedly when encountering a new star's warmth. Perhaps their long journey through interstellar space, bombarded by cosmic rays, exposed to harsh radiation, alters their surface chemistry in ways that affect outgassing patterns when they finally enter another solar system. These ideas spiral towards speculation, but they emerge from genuine uncertainty about conditions beyond our cosmic neighborhood. Humanity has visited only one star system, ours. Everything beyond remains inference from photons collected across light years. When visitors from that beyond arrive and behave strangely, the strangeness might reveal not error but difference, variations in cosmic chemistry playing out in unexpected trajectories. The investigation phase doesn't close, it pauses, suspended by lack of data. The comet has gone. The telescopes track other targets, but the numbers persist in archives, waiting for context that future discoveries might provide. Perhaps the next interstellar visitor will clarify patterns. Perhaps it will deepen confusion. Either outcome advances understanding by constraining what's possible in a universe far larger and more varied than the small sample accessible from Earth's surface. For now, 3 Atlas remains what it was, a traveller from beyond, briefly measured, imperfectly understood, carrying implications about cosmic diversity that won't resolve until many more such objects cross humanity's observational threshold. The data is good, the explanations are provisional, the mystery is contained but not solved. Astronomy operates at the boundary of what's knowable. Every observation captures light that travelled for seconds, years, or millennia before reaching the telescope. The universe reveals itself not directly, but through electromagnetic messengers that encode information in wavelength and intensity. Decoding those messages requires instruments, mathematics, and assumptions, layers of interpretation standing between raw photons and understood phenomenon. 3 Atlas represents this condition perfectly. The comet existed as physical object, rock and ice shaped by processes in another solar system. But to astronomers, it existed primarily as data. Pixel values in CCD images, photon counts in spectra, coordinates measured against star positions. The object itself remained remote and unreachable. Knowledge about it filtered through instruments and models, each step adding precision and uncertainty in equal measure. This isn't failure, it's the nature of the discipline. You cannot touch a comet moving through the outer solar system. You cannot sample its ice directly or measure its mass on a scale. You infer these properties from how light reflects, how trajectories curve, how brightness changes with time and viewing geometry. Each inference carries error bars, quantified uncertainty that honest science acknowledges and incorporates. The acceleration that puzzled researchers stemmed not from inadequate physics, but from insufficient data. Given perfect knowledge of the nucleus composition, size, shape, rotation, and surface properties, the non-gravitational forces would calculate precisely. But observations provided only fragments of this information. Brightness without size, spectra without abundance measurements, position without interior structure. The model inputs remained estimates, so the model outputs remained approximate. Yet within these limits, understanding emerged. The acceleration magnitude fell within ranges typical for cometary outgassing. No exotic physics required explanation. No violations of conservation laws appeared. The mystery was quantitative. How much gas, what composition, which surface regions active, not qualitative. This distinction separates the understood but uncertain from the genuinely inexplicable. Consider what astronomers did determine definitively. 3 Atlas followed a hyperbolic trajectory, confirming interstellar origin. Its velocity at infinite distance exceeded the solar system's escape velocity by a margin that allows calculating the comet's path through the galaxy before encountering the Sun. Backtracking that path suggests possible birth systems, though uncertainties grow large over millions of years of galactic motion. The comet came from somewhere out there, a direction now known, even if the source star isn't. Spectroscopy revealed carbon compounds in the coma, specifically diatomic carbon, C2, and possibly cyanogen, Cn. These molecules indicate organic rich material, similar to solar system comets but not identical. The exact ratios differed slightly from typical values, hinting at formation conditions with different temperatures or chemical abundances, subtle variations that suggest diversity in planetary system chemistry across the galaxy. Photometry showed the comet's brightness varied periodically, likely due to rotation. The period appeared to be several hours, typical for small bodies but useful for estimating shape. An elongated nucleus tumbling end over end would show larger brightness changes than a spherical one. The data suggested moderate elongation, making 3i Atlas a somewhat irregular object rather than a perfect sphere or extreme cigar shape. Each measurement added detail. None resolved ambiguity completely. This incremental accumulation characterizes astronomical knowledge. Certainty builds slowly through multiple observations, different techniques, and consistency checks across independent datasets. A single observation of anomalous acceleration launches investigation. Dozens of observations from different sites constrain the effect. Future detection of similar objects will contextualize whether 3i Atlas represents typical interstellar behavior or an outlier. The process mirrors broader scientific epistemology. Knowledge isn't binary, known versus unknown. It exists as probability distributions, confidence intervals, and degrees of belief calibrated to evidence strength. Physicists don't doubt gravity's existence, but they quantify uncertainty in the gravitational constant to many decimal places. Astronomers don't doubt 3i Atlas accelerated, but they remain uncertain about which specific mechanism dominated among several viable candidates. This uncertainty doesn't justify equal credence for all explanations. Outgassing remains most probable because it requires the fewest additional assumptions and matches known physics. Exotic alternatives, dark matter interactions, previously unknown forces, remain possible in principle, but unsupported by necessity. When conventional explanations suffice, invoking novel phenomena constitutes poor reasoning without additional evidence demanding them. Yet the experience of encountering Oumuamua's more dramatic acceleration tempers confidence. That object sparked significant debate, with some researchers arguing for exotic explanations including, however speculatively, artificial origins. The physics community eventually settled on outgassing as most likely, though not unanimously or with complete satisfaction. The discussion revealed how even expert consensus contains gradations of certainty, with some findings accepted provisionally pending better data. 3i Atlas adds a data point to an emerging pattern. Interstellar objects show non-gravitational accelerations that challenge models. Whether this reflects true compositional differences, observational selection effects, or modelling inadequacies remains uncertain. 3 objects constitute insufficient statistics for firm conclusions. Science requires larger samples, but finding interstellar visitors requires sky surveys scanning vast areas continuously. Expensive, technologically demanding projects that detect only the brightest or closest objects. Future surveys promise improvements. The Verity-Rubin Observatory, scheduled to begin operations in Chile, will scan the southern sky repeatedly with a camera capturing unprecedented detail. Simulations suggest it might detect dozens of interstellar objects annually, transforming rare anomalies into statistical populations. With larger samples, patterns become distinguishable from noise. Anomalies that persist suggest genuine phenomena. Those that disappear into expanded datasets reveal selection biases or chance clustering. Until then, 3 Atlas remains a singular case study. Valuable, but incomplete. Its trajectory documents one possible behavior of objects shaped in another, star system, and subsequently released into interstellar space. How representative this case might be awaits comparison with many more examples. The comet itself has departed, passing Mars's orbit outbound, receding into the cold and dark from which it came. Its motion will carry it eventually out of the solar system entirely, returning to interstellar space at a velocity altered by the Sun's gravity and whatever forces acted during perihelion passage. In some distant epoch, it might enter another star system. Astronomers there, if any exist, might detect it, measure its trajectory, and puzzle over its behavior as humanity's astronomers did. They would face the same challenges: inferring properties from limited observations, modeling motion with incomplete inputs, distinguishing signal from noise in sparse data. The universe reveals itself reluctantly, maintaining mystery not through active concealment, but through sheer scale and distance. This perspective offers comfort and frustration in equal measure. Comfort because mysteries that result from insufficient data admit eventual solution as technology improves. Frustration because improvement occurs slowly, constrained by economics, engineering, and the fundamental limits of gathering photons from faint, distant objects. Astronomy advances incrementally, not through sudden revelations but through accumulated observations that gradually sharpen fuzzy pictures into clearer focus. 3i Atlas contributed its measurements to this ongoing process. Hundreds of images, dozens of spectra, orbital elements calculated and refined, non-gravitational parameters estimated and debated, all archived in databases accessible to researchers worldwide. Future studies comparing interstellar objects will reference this case, extracting its data for meta-analyses that might reveal patterns invisible in individual observations. The comet's passage through human awareness lasted roughly 8 months, from discovery in December 2019 to fading beyond detection in late 2020. Within that window, dozens of professional astronomers devoted portions of their careers to studying it. Telescope time was allocated, papers were written, conferences included presentations discussing the results. The scientific community mobilized around this visitor, extracting every possible measurement before it vanished. What remains is memory encoded in data, numbers preserved electronically and in print, orbital elements characterizing a path through space, uncertainties quantifying what wasn't determined, interpretations flagged as provisional pending future evidence. This represents astronomy's response to the cosmos: systematic observation, careful analysis, honest acknowledgement of limits. The silence surrounding 3i Atlas now isn't the silence of mystery unsolved. It's the quieter uncertainty of questions awaiting context. The data exists, the anomaly is documented, the explanations remain plausible but unproven. This state of knowledge, partial, provisional, pending refinement, characterizes much of science operating at frontiers where phenomena exceed current instrumental capability. And so, the numbers wait in archives, inert but not meaningless. They preserve what was measured during those months when an interstellar visitor passed close enough to resolve partially. They document motion that didn't quite match models. They quantify acceleration that required explanation astronomy hasn't definitively provided. Somewhere in deep space, 3i Atlas continues its journey. The acceleration might persist, driven by sublimating carbon monoxide still warm enough to outgas. Or it might have ceased, the comet's surface recooling to dormancy as solar distance increases. No one watches anymore. No telescope follows its faint light through the dark. The object has returned to anonymity, one iceball among countless trillions drifting through interstellar space, unobserved and unremarkable except for those few months when it happened to pass close enough to Earth that instruments could measure it imperfectly. The data matched nothing precisely, and yet it repeated patterns seen before in other unexpected accelerations, suggesting not error but complexity in phenomena still incompletely understood. The comet asked questions with its motion. The answers remain partial. The investigation continues, though the subject has departed, leaving only echoes in archived observations and the certainty that more such visitors will come, each carrying new data toward eventual understanding that accumulates across observations, objects, and decades of patient watching.